Hello, in this video we want to look at the average value of a function. And we're going to use some calculus to figure out how we can do that for a continuous function. We're going to build on what we know in the discrete setting and translate that into the continuous setting. You'll do this a lot with applications of integration. This is a good one to get started with. So let's see what happens. So let's suppose we wanted to find the average of the following set of numbers that we have here. 5, 16, 27, 32, and 25. Looks like they're chosen at random. We'll see if they come back to us later. The way we do this before calculus, not using anything that we've learned in this area, just using what we knew before, is we add these numbers. Let's take 5 plus 16 plus 27 plus 32 plus 25. We add all those numbers together, divide by however many we have. We have 1, 2, 3, 4, 5 in total. And that's going to give us our average. We can figure out what that is if we take the time to add these numbers up. It looks like I've got 25 and 5 is 30. Let's call that 62, 43. I believe this is 105 over 5. And we can reduce that. In this case, things worked out pretty nicely in terms of fractions and whole numbers and so on, and we end up with 21. So no calculus necessary for this part, but we want to use this same idea to come up with an estimate for the average value of a continuous function, taking on all those values, and see from that estimate if we can get the exact value. So let's suppose now we want to find the average value of a function over an interval. In this case, our function is a nice polynomial function. F of x equals negative x cubed plus 3x squared plus 9x plus 5. And this is on the interval 0 to 4. Now, one thing we might note here at the bottom, we said f of 0 is 5, f of 1 is 16, and so on and so on, those different function values. You can verify that for yourself if you like. Those are exactly the numbers that we had from before when we had our discrete example. 5, 16, 27, 32, and 25. So we're going to tie it back into that example from just a few minutes earlier. So here's what this function looks like over the interval in question. We're running from 0 to 4 over there. We want to find this average value. Now this is a trickier problem because this function is continuously varying, as we see. If it were a constant function, it would be very manageable. If it was 15 everywhere, well, the average value would be 15. If it was changing at a constant rate of, if the function was changing at a constant rate of change, it would be a linear function. That would be easy as well, relatively speaking. But what we have here is something that's a little bit trickier. So to get started, we might try an estimate. We're looking at our function values there. We notice that there's 5. That would be 16. Here we've got 27, 32, and over on the end here, 25. So we know the average value of those 5 values is 21. That actually looks like it's about a good average value for that function. If you go across 21, it looks like about half the area is above, half is below. So that would balance out to, looks like a constant function somewhere near there. So that's a reasonable estimate. If we wanted to get a better estimate, one approach we might take would be to use more function values. Maybe we try, instead of at f of 0, f of 1, f of 2, we try f of 1/2. Include f of 1.5, include f of 2.5, and so on. We would get more points, we would have more function values, we were adding more things together, but we would divide by a larger number. So, building on this idea, we could use more and more function values, add them together, and then divide by the total number of values that we chose. With this in mind, it gives us an idea for the average, for the estimate of the average of the function on that interval. So my average value of f would be estimated by a sum of as many function values as I like and then just divide by the total number of function values I used. So this x1, x2, so on up to x sub n, these would be all values within the interval 0 to 4. So we might try, for example, f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 all over 5. We don't have to go through and do this computation because we already did it. We said f of 0 was 5, f of 1 was 16, and so on. We saw that this was, from before, 21. So that's our first estimate for the average value of this function over this interval. Okay, so that estimate, that example, first example just disappeared. We want to talk in general about how we might try to find this average value. So keeping this expression in mind, we note the following. When we're talking about integration things, our little steps, our little constant increments in our changes in x are given by the following: b minus a over n. Or if I like, delta x over b minus a equals 1 over n. And so with that in mind, this expression can be rewritten as f of x1 plus f of x2, adding all these up, and now instead of dividing by n, we would multiply by delta x, all that over b minus a. Our 1 over n is the same as delta x over b minus a. And if we like, we could rewrite this one more time as 1 over b minus a times f of x1 delta x plus f of x2 delta x all the way up to f of xn delta x. And now we're getting somewhere. Now we see this 1 over b minus a times this expression. This is a Riemann sum. Okay, so we paused for a minute to clear this up. We moved what we had down here up to the top. But again, we want to reiterate. What we have for the average value of a function on an interval, it's estimated by this 1 over b minus a. That's the length of the interval, b minus a. So you're dividing by the length. And what we have here is a Riemann sum. And so this leads us to the main idea of this section. It leads us to our formula, and we took all this time to derive it to try to make sense of it. So that's the following. The average value of f on the interval a to b, and we have in mind that f is continuous. The average value of f on that interval is 1 over b minus a times definite integral from a to b of f of x dx. So we compute the definite integral over that interval just like we've been doing. If you divide by the length of the interval, that gives you the average value. Again, we build this up using an estimate that we know in the discrete case. In case for us, finding the average of a discrete set of numbers. We use that for our estimate. We let limits do their work. We have our Riemann sum, and out pops a definite integral. Let's go back to that previous problem and see if we can find out the exact average value of that function on the interval. So again, we're looking to find the average value of this function, this third degree polynomial function on the interval 0 to 4. We've just seen a formula for how to compute that. Let's apply it. So my notation here is f sub avg for the average value of f. I don't know at face value right here what the interval would be, but it's clear from the context when you do these problems. So I've got 1 over 4 minus 0. Definite integral from 0 to 4 of this function. Negative x cubed plus 3x squared plus 9x plus 5. Working through the integration. We have negative 1/4 x to the 4th plus x cubed plus 9/2 x squared plus 5x, and we're running from 0 to 4. So now we do the evaluation, evaluating at our upper limit of 4. Well, 4 to the 4th divided by 4 is just 4 cubed, so I've got negative 64 plus 64. 4 squared is 16, divided by 2 is 8, times 9 is 72, plus 20, minus 0 plus 0 plus 0 plus 0. Minus 64 plus 64. We lose that. We end up with 1/4 92 times 92, excuse me. And if we want to take that a step further, we end up, that is an integer value, we have 23. So in the discrete case, when we had those 5 numbers and we took the average, you may remember that our result was 21. That was our estimate for the average value of that function. 23 is our exact value. That's the average of this function over the interval. So let's remember this. Our first estimate was 21. Our exact was 23. I want to go back to the graph to try to make sense of this. So again, we see our graph here over the interval 0 to 4. Here's that third-degree polynomial, the part of it that we're interested in. We found the exact average value is 23. So if we were to look at 23 and take this across, half the area above would equal that. Sorry, the area above would equal the area below. The average value is 23. Not far off from the 21 that we found with our first estimate. We might think about, or might wonder why the exact value is a little bit higher than our estimate. And if you look at this, it seems like we've got a little bit more of the larger values over here. So we're getting, if we were to include more and more function values, we'd be getting more and more values above 21. And so just looking at how that behaves, the 23 shouldn't be so surprising. The fact that it's exactly 23 we wouldn't expect, but something bigger than 21, seeing how this behaves, is not too surprising. So that's how we find the average value of a function. Again, to remember what we need to do, it all comes down to a simple formula. We spend a lot of time building up to this formula, deriving it and showing why it works. In the end, you need to know the formula. The hope is that you'll understand, have a good understanding with why this works. And so when you have problems with a little bit of a wrinkle, you'll be able to manage that. But this is your formula, nice, short and sweet. Again, something that we build up from our model in the discrete case to use as an estimate. From that, we get our definite integral.